Hi, everybody. Thanks again for joining us for the latest in our series of Google Hangouts with Sigma Xi's distinguished lecturers. We really appreciate you coming. This particular Hangout is sponsored by the Research Triangle Park chapter of Sigma Xi, so hello to all those members. You can ask questions during this lecture, this Q&A. There's a question bar on the right side of your screen, or you can tweet questions to us using the hashtag AmSciGHO. AmSci Google Hangouts. So today we are really very fortunate to have a really informative discussion about math, which some of you may not think is interesting, but I promise you will by the end. So today we have Richard Canary, who is a professor at the University of Michigan. Thanks so much for joining us.
Oh, thanks for inviting me.
So one of the questions I thought we might start out, just a little bit of an icebreaker in case you don't, hope you don't mind, but I think a lot of people have a sort of a Hollywood impression of how mathematicians work, that you're standing around in a room with a whiteboard and a bunch of colored markers and just, you know, kind of using numbers and symbols. Is that an accurate view of what you do when you're brainstorming, or do you mostly use computer these days, or what do you do?
I'm probably mostly sitting on my couch, actually. So, yeah, it depends. There's a lot of different things that go into it. For me, I really like to collaborate with other people. So a lot of my time is spent, talking with my collaborators. Now, of course, my collaborators are mostly not here at Michigan, so I'll be sitting alone and thinking, but then it's important to me to talk to people too. So those are probably my, two biggest forms of doing math.
Right. Okay. So it's sort of more of a thought experiment in that sense.
Yeah, we draw a lot of pictures too. I'm a topologist, so it's a lot of drawing of pictures and diagrams, which may not make sense to most people when they see them, because we have our little shorthand for what things mean. But yeah, that's mostly what we're doing.
Right. Okay. So you mentioned you're a topologist. I wonder if maybe you can tell people exactly what that means and why that particular area of mathematics was of interest to you.
Okay, so topology, I'm really sort of in between geometry and topology. So in geometry, we sort of measure things, right? We sort of care about what are the distance between 2 points, what's the angle between two line segments. And in topology, we're interested in classifying things, but we don't care so much about their shape. So the classic one is that to a mathematician, the coffee cup is the same as a donut. But so topological properties are properties that are the same of a space if you just, you bend it around and stuff, but you're not allowed to tear it. Whereas geometric properties are properties which really keep track of distances between points. And so if you start, bending, you're going to be changing those distances. So to geometer, a coffee cup and a donut are quite different. And in fact, often spaces I study are the space of all possible different geometries on the same underlying topological space.
Okay. Can you talk a little bit about why that's interesting to you, is in all of the areas of math that you could have gone into? Why did that one particularly grab you?
Well, I think for a lot of people, it was just that's what I encountered, and I had some very, charismatic and engaging mentors that got me interested in it. I think there's maybe a lot of areas I could have ended up in, and though I think the sort of intuition I have is well suited towards geometry and topology, and some people find that more algebraic or more analytic things come more naturally to them. So this was an area which it felt more natural to my way of thinking.
Right. Okay. Do you think that being in a field like topology requires good spatial envisioning, or is that separate from what you do?
Yeah, I think you do need, having a good spatial intuition helps with topology, and it also will develop your intuition. So if you don't start with it and you start working in topology, you'll get it.
Right. One of the other things you've talked about before is sort of the difference between mathematics and physics. I wondered if you might talk about that, sort of how you define the difference between the two.
Oh gosh, I actually don't know very much about physics, but sort of physics and mathematics grew up together, really, right? Because, sort of mathematics was developed as a way to describe physical phenomena. So most prominently, of course, calculus. But even now, the sort of tools that we're developing in topology have applications in physics. So, for instance, the sort of mathematics I do, which is studying geometric shapes on surfaces and three manifolds, has had a lot of applications within string theory, which was a very popular field within physics, especially about 10 years ago. So,
right. In sort of these classic jokes about the difference between mathematics and physicists, one of the things you talked about was, if a room was on fire and the mathematician woke up and he saw that there was water there, he'd be happy to go back to sleep because he knew there was an answer, not necessarily had to do anything about it. So
right.
There's a lot of different jokes about the nature of solution in the difference between math and physics.
Right. Do you want me to tell that joke?
Oh, sure. Go ahead. You're probably better at it than I am.
Well, you got the punchline already.
Oh, I'm sorry.
So, I mean, he's supposed to be the engineer, the physicist, and the mathematician, right? And
right. Okay.
the engineer wakes up, there's a fire in his room. He goes over, he notices that there's water. He grabs some water, he throws it on the fire, puts it out, goes back to sleep. The physicist wakes up, there's a fire, and he, does a quick calculation of exactly how much water he needs and what angle he should pour it at, pours the water on the fire, and goes back to sleep. Mathematician wakes up, notices there's a fire, knows that there's water, does the calculation, goes back to sleep, satisfied there's a solution.
Right. Right. Okay. And one of the other things I've heard you say before is that, with physics, what you're trying to do is you're already living somewhere and you're trying to figure out the rules of where you're living, versus math is taking the rules and figuring out what it's like to live there in a different topology, maybe.
Right. So, we have the freedom, in physicists, if you're a physicist, it maybe doesn't make much sense to study a space which doesn't actually correspond to our reality. But in mathematics, we have the freedom to impose any conditions on a space we want and go ahead and study it. And later on, that sort of thing may end up being useful in physics, or it might not be. There's this tremendous interaction where mathematicians do things which do not look at all useful. And then 90% of the time they're not. But then, that 10% of the time can be very valuable. For instance, number theory was originally thought of as the purest of all mathematical fields, and now it's perhaps the most useful of all mathematical fields, especially if you're a computer scientist.
Now, number theory, is that related to cryptography and things like that?
Right. So number theory is what underlies cryptography. Most of the codes, for instance, which allow us to send data securely over the internet are based on number theoretic things. They're based on the fact that it's very hard to factor a large number into its prime decomposition, into a product of primes. Even though we know we can, actually doing it is difficult. And so that vastly oversimplifies what cryptographers are doing, but at the core of that's at the core of sort of modern cryptographic theory.
Right. Okay. And we may get back into whether or not usefulness is a good measure for math later. But let's go back to what you were saying about mathematicians can basically define the space they live in, or any hypothetical space. But can we talk about how we defined the current space that we live in as we know it in what's called Euclidean space?
Guess I'm not exactly sure what you're getting
well,
at.
I guess before we get into sort of the more theoretical areas you talk about with hyperbolic space, can we go ahead and define for people like Euclidean space what it is that we actually live in as we picture it right now?
Right. So we're thinking of ourselves as living in a three-dimensional space, and then we have a distance formula, right? And we know that. That if you take the distance between, point A and point B, is the length of this line segment joining point A to point B. And we have a way of measuring the distance of that line segment. And, if you know calculus, the way you do is you travel along that line segment and you integrate the speed. you've traveled, or you can approximate it. Like, if you go if you have in each minute, you say, well, I went about 30 miles per hour that minute. I went about 40 miles per hour that minute. Then you can sort of estimate how far you've traveled.
Right.
So we have a notion of measuring length for Euclidean space.
Right. And one of the sort of the main definitions of Euclidean space has to do with the shortest path between 2 points. Is that right?
Right. So again, now when we do hyperbolic space, there's a lot of different models for hyperbolic space. What we're going to do is we're going to define a different notion of speed.
Right. Okay.
And so that is going to allow us, if we're traveling from point A to point B in hyperbolic space, then we can sort of measure the total distance traveled in hyperbolic space, and the distance between those 2 points from the hyperbolic space viewpoint is the length of the shortest path joining them again.
Right. Okay. But I'd like to give a little bit of history of hyperbolic space before we get into it. But as I understand it, tell me if I've got this right. One of the other aspects of Euclidean space where we live right now is, for instance, if you take just a circle as an example, the area of a circle grows exponentially, and it grows much faster than the circumference of the circle. Is that correct?
Well, actually, the area of a disk grows quadratically.
Okay.
It's pi r squared, right, is the formula. And the circumference, which is just a fancy word for the length of the circle of radius r, is 2 pi times r. So it grows what we call linearly. So for instance, if you're a circle of radius 3, your length is 2 pi times 3, which is a little less than 20, and then the area you bound is pi r squared, which is a little less than 30. I don't know.
Right. Right.
So but as that grows, sort of r squared grows a lot faster than r.
Right. Okay. And if you're looking at a circle in Euclidean space, most of the area of that circle, I think you said, is in the middle of the circle and not at the boundary. Is that
right? So there's a lot of area everywhere. So if you're within distance 1 of the boundary, so you have suppose you have a gigantic circular fence, and you might say that, okay, how much area is within a foot of the fence? Well, that's roughly the length of the boundary, which is 2 pi r. But then the total area is pi r squared, which is much bigger. So there's a lot of area which is not within a foot of the fence, or not within, several feet of the fence.
Right. Okay.
We'll see in hyperbolic space that's different.
Right. So let's get to hyperbolic space now. I'm wondering if first you can kind of describe the origin of that term. Maybe give us some history of who came up with hyperbolic space to start with.
Right, so the people who were the first reason people were interested in hyperbolic space grows out of Euclid's axioms. Euclid defined 5 axioms for geometry, and the 5th axiom, well, he had a more complicated statement, but it's equivalent to what's called the parallel postulate, which says that if you have a point and then you have a line, that there's a unique line. I'm not sure how useful this may be. Draw like that.
Right.
I don't know if you can see that. Right. You have a point and you have a line, and then there's a unique other line through this point which doesn't intersect this other line. So there's a unique parallel line through that point. And a lot of people thought that, probably that followed from his first 4 axioms. And so if you go back to the 19th century, this was something that or 18th or 19th century, this is something that a lot of both serious mathematicians and amateur mathematicians were interested in. For instance, Lewis Carroll devoted a lot of energy to this issue. So the first reason for hyperbolic geometry developing was that it's a geometry which satisfies Euclid's first 4 axioms, but which, if I give you a point and a line, there's lots of hyperbolic lines which do not intersect that other line.
Right. I don't know if this is the one you're talking about, but I printed out one of your pictures.
Oh, there we go. That's right. There we go.
Right.
So that's a model for hyperbolic space where it's everything inside the unit disk. And then it turns out that in that model, the lines, or the fancy word is geodesic, but the lines are just the curves such that they're the shortest distance between 2 points is realized by traveling along that curve. They're exactly what are arcs of circles which are perpendicular to the boundary. So if I give you one of these lines and I ask you how many arcs of the circle perpendicular to the boundary pass through this point but don't intersect this line, well, there's an awful lot of them, as you saw in that picture.
Right, okay. And I don't know if you can describe I think there were a couple of mathematicians who were initially responsible for developing some of these theorems. Is that correct?
Right, so there was, Gauss apparently had understood that this existed, but had decided not to publish it because it was a very controversial thing at the time. And Bolyai and Lobachevsky were the first two to publish it, I believe.
Right. I gather they were fairly obsessed with this topic too, based on some of the commentary you've mentioned from their families about.
Right, so in fact, Bolyai's father, I think, I got to remember my history here. I should have brushed up on my history.
That's okay, yeah.
Bolyai's father had spent a lot of time trying to prove that the parallel postulate did follow from the first four. So that hyperbolic space could not exist. And so he cautioned his son heavily not to go into this.
Oh, okay. So he had personal stake in this as well.
Yes.
Interesting. Okay. Yeah. So mathematical wars within the family. Just to give people a little bit more of a visualization of the space that you're talking about, one of the examples you've given is an Escher tessellation, where in that case he used fish within a sphere.
Right.
You have larger fish in the center and get smaller and smaller towards the edge. If you could sort of imagine those fish staying the same size throughout the sphere, that would kind of give you a sense of hyperbolic space. Do I have that right?
Right, yeah. So Escher had several drawings which are sort of modeled on hyperbolic geometry. And so the one you're mentioning is a tessellation of hyperbolic space by fish. So from the hyperbolic viewpoint, if you put your hyperbolic goggles on, all those fish look exactly the same size, even though if you're using Euclidean goggles, it looks like they're getting smaller and smaller and smaller as they get closer to what looks like, to our Euclidean eyes, the boundary of hyperbolic space.
Right, okay. Now, I only have a black and white of this one, but I printed it out just so people could give a sense of that one. So we got circle fish here. So just quick little demo there. So were the people who were looking into hyperbolic geometry simply doing it to try to disprove Euclid, or was there another reason for working in this area?
Well, there were people working on it from both sides. Some people wanted to, prove that the fifth axiom did depend, and some people wanted to prove that it didn't. So they were trying to settle the question. I mean, it had something of the feeling of maybe, well, Fermat's last theorem had really caught the popular imagination in the 20th century. And a lot of people, both very serious professional mathematicians and also amateur mathematicians, would be thinking about this because it was a very accessible problem you could think about. So by the middle of the 19th century, it started to become clear that hyperbolic geometry was going to be useful for other things as well. And this sort of realization maybe goes back to Riemann and then was made even more powerful by people like Klein and Poincaré at the turn of the 20th century. And they realized that the hyperbolic geometry could be used to model surfaces of higher genus, or surfaces with holes in them. So it turns out that there's 3 geometries, natural geometries in 2 dimensions, and one is the sphere. You can think of the sphere as a geometric object. There's a notion of lines. Those are just great circles, and there's a notion of angle, and you can talk about geometry on the line, and of course the sphere itself very naturally has spherical geometry. And you can also talk about Euclidean planar geometry, and it turns out the torus naturally has Euclidean planar geometry. And if you're my age, you grew up with video games which were played on the Euclidean torus. So in the old-fashioned video games, you would go off the right side of the screen and come back in the left, and you go off the top and you come back in on the bottom. And if you thought about what you were doing, it was as if you had taken the top of your screen and joined the top to the bottom, and then taken taken the left side of your screen and glued it to the right side of the screen. And so you would get a torus, which is like a donut with the surface of a donut with one hole.
I think you've just blown the minds of a lot of old gamers by saying that, but yeah, definitely, I see what you mean.
So I mean, this had to do with memory, right? Nowadays, we have lots of memory, and the world goes on forever. You walk to the right side of the screen, and the screen moves, and you're in a new part of the world. But in the old days, yeah, there wasn't much memory, so everything had to happen in a very small space.
Right. So maybe we can also talk about how the hyperbolic space differs from what we just talked about before with the Euclidean space in terms of the shortest path and area versus circumference. How do those differ?
Right. So the word hyperbolic, you sort of asked me earlier, and I didn't really answer why the word hyperbolic. So we got into the history. And hyperbolic is one of these incredibly overused words in mathematics. We apply it to a lot of different things. But one thing you always see when they're the word hyperbolic is you see exponential growth or exponential decay. In the case of hyperbolic space, you see that in that if you look at the length of a circle of radius r, it's 2 pi times the hyperbolic sine of r. And, so if you don't know what the hyperbolic sine of r, you can see that's roughly pi times e to the power r. So e is a number, it's about 2.7. So you keep raising it to the power r. So for instance, if you look at a circle of radius 30, it only has length about 100 in Euclidean space. But if you take a circle of radius 30 in hyperbolic space, that's roughly length pi e to the 30. So if you raise 2.7 to the 30th power, that has, more than 10 digits, for instance. So you can see you're comparing something which is, did I say 30 times 2 pi was roughly 90?
Yeah.
Yeah, that's 30 times 2 pi is like right around 200, right? Because pi is about 6.28. Yell at me if I do things like that.
Sorry, we don't mean to put you on the spot.
So it's roughly 200. Whereas, if you look at the area in hyperbolic space, even at just a circle just radius 30, it's not that big a number. The length is got more than 10 digits.
Right. Okay.
And the area of a circle of radius r is, again, it's the exact formula is 2 pi times the hyperbolic cosine of r minus 2 pi. But again, just roughly, that's about pi e to the r again. So in fact, the area here, and the length are roughly the same. I mean, their ratio is going to 1, and the difference between them, in fact, is going to 0. So the area enclosed by a circle of radius 30 has roughly 10 digits.
Right, okay.
If you think about what this means, for instance, for real estate, everybody can live near downtown.
Right, okay.
I mean, there's tremendous, if you're willing to go 300 feet from downtown, there's unlimited amount of virtually unlimited amount of real estate within 300 feet of downtown.
Right, okay. So the difference here, you're saying that the area and the circumference grow at approximately the same rate, and a lot of the area of the circle, whereas before we're saying most of it's in the center, it's more near the boundary. Is that right?
Yeah, so if you think about the same thing, if you're out near the boundary, and if you're within a distance 1 of the boundary, well, that area is roughly 1 times the length of the boundary. So it's roughly pi e to the r again. Right. That's very rough. So I mean,
right, of course.
But would yell at me because I'm being a little rough. But anyway,
right.
That's a large proportion of the boundary of the areas within distance 1 of the boundary. So if you have a giant pen full of say cows, then almost all the cows are at the fence line.
Right. Now, you were saying that, as something is sort of defined as hyperbolic if it sort of continues on and doesn't quite hit a boundary. So does that mean that the path that you were saying before, from, say, the center to the edge in Euclidean space, that's a limited distance, but in hyperbolic space, that essentially just never quite reaches the end of the boundary. Is that right?
Right. So one model for hyperbolic space is you take everything above the x-axis, and then you change the speed by saying that if you're going at speed 1 at height t, then the speed Euclidean speed 1 at height t, your hyperbolic speed is 1 over t, which means that if you're that means that as you approach the boundary, then if you go from, say, height 1 and you try to go all the way down, straight down to the boundary, you're integrating 1 over t from 0 to 1. We know that blows up. That goes to infinity.
Right.
Or if you think about, if you're approximating, you're summing up 1 plus 1/2 plus 1/3 plus 1/4 harmonic series. We know that adds up to infinity.
Right. So you never quite get there.
Right. So even though it looks to our Euclidean eyes like it's, like if we're standing at height 1 here in hyperbolic space, we have our Euclidean goggles on. It's only a distance 1 to the boundary. But with hyperbolic goggles, the boundary is just off infinitely far away from us.
Right. So I think that you've developed a couple of analogies to try to help people understand the difference between these two spaces and how things might behave and move differently. And you've actually developed some sports metaphors to kind of give people a better sense. I wondered if you could talk about, before we get into the specifics, why you were looking at sports in this case to make it more applicable to what people can understand. Was it just that, you didn't want to have the classic math word example of, 2 trains traveling or something like that?
Well, partly I think it has to do with the people who raised me as a mathematician. So I was, as a graduate student, I worked with Bill Thurston, who's sort of famous for his geometric intuition and famous for also teaching all of his students, including me, to try to get a very visceral understanding of the space. So what is it like to live in the space? So that sort of was the basis for it. I said, okay, what is it like to live in this space? So one analogy is like when I started talking about real estate. What would this mean for, the fact that the area is growing incredibly quickly, exponentially? What does that mean? It means that everybody's near downtown. There's a huge amount of space near downtown is one way of thinking about it. And I just started thinking about what are other things we could do. What would golf or baseball, or I think the third one I usually talk about is beach ball. And right. I gave a talk and it seemed to work pretty well. So I've developed a talk which has grown into the talk that I give as part of the Sigma Chi Distinguished Lecture Series. And I've given it as a math club talk in the past, but I've also gave it for Saturday morning physics, which is sort of and that version of it's online somewhere, which is for high school students and for people in the area just interested in physics, and public science lectures. It turns out to be a pretty flexible way to explain things. And
I should mention to people who are interested in that, we did actually post a link to that on the event page, so you can find that there. So, so let's talk about some of your sports analogies. I'm just going to go back to this, one picture where you've got all these different lines here on the edge of the circle to talk about. These are the lines we're looking at in hyperbolic space, and those curved lines are actually the shortest paths in hyperbolic space. Is that correct?
So if you're trying to get from point A to point B in hyperbolic space, you're going to ask, what's the shortest path from this hyperbolic viewpoint? And because traveling near the boundary has this high cost, because when you go near the boundary, the closer you get to the boundary, the faster your speed is. Well, it turns out that it's quicker to sort of bend back towards the center and then come back out. So you see these arcs of these circles. There's circles perpendicular to the boundary. If you go from A to B, you travel along here and then back down to there. And it turns out that's the best thing to do.
Right. So this is efficient thing to do. This is different than Euclidean space, where the shortest distance between 2 points is always a straight line. So
it's what looks. So if you're wearing your Euclidean goggles, our straight lines are what we think. We're used to them calling them straight lines. But if you put your hyperbolic goggles on, now you'll see that what looks like a straight line is this path, which is these semicircular paths.
Right. Okay. So right.
Yeah, which you got to toggle back and forth. Yeah.
Right. Okay. So with my hyperbolic goggles on, a curved line is actually a parallel line in that case.
It's straight. Yeah, it's totally straight. It's I mean, what we mean by a straight line is that it is the shortest distance between any 2 points on a line. And sometimes
Right.
if you're asked to define what a line is, you start thinking for a while, like, what's a line? What's a line? It's a line. And there's what actually defines that? Well, you could write down a formula, or you could say, oh, it's the shortest distance. It's the shortest path between 2 points. So.
Right. Okay. So let's go through a couple of your analogies here. Do you want to talk about your baseball example?
Sure. So usually one of the first things I talk about is baseball, and a question you might ask yourself is, if you're in hyperbolic space, I may have spoiled the answer a little bit already because we talked about how big hyperbolic space is, but how many outfielders might you need? And you're probably gonna guess a lot. But you can actually do a little bit of a thought experiment with the calculation. So you can, if you do the calculation in Euclidean space, I usually use sort of an idealized baseball field, where the outfield is 300 feet all the way around, and the infield is 100 feet all the way around, and the baseball diamond is a perfect quadrant. And then the area of the outfield in that model is, I think, around 62,000 square feet. So you might guess every outfielder can cover about 20,000 square feet. And so then you can go do the same calculation of what's the area in hyperbolic space. Well, it's the area of disk of radius 300, which is roughly pi e to the 300. Well, that has over 100 digits. And then you subtract off the area of the infield, which is pi e, which is rough. Oh, you should divide by 4 too, because you have only a quadrant. You don't have the whole thing. And then you subtract off the area of the infield, which is roughly pi over 4 e to the 50. And the result still has more than 100 digits. And so if you figure every outfielder can cover 20,000 square feet, then you need at least 10 to the 100 divided by 20,000 outfielders. So at least 10 to the 95th.
Well, that's a lot of outfielders.
That's a pretty big number. Yeah, my favorite joke about this is that if you want to make a Disney movie about having a family big enough to field a baseball team, you can't do that in hyperbolic space.
No, that'd be a lot of people. I think everybody who ever wanted to enter Major League Baseball probably would get in.
Right.
Okay. So one of the other things you talk about is a sort of target distance in golf. If you're hitting golf ball and you miss the hole by even just 1 degree, what difference that is between Euclidean and hyperbolic space.
Right. So here the example is, suppose you're 100 yards from the hole, 300 feet, and you hit the ball exactly 100 yards, but 1 degree off. Well, that's pretty good. That's a lot better than I can do, and I think it's a lot better than most of us can do. And so you can figure out exactly what that is, or we can sort of estimate it. Now, if you're estimating it, well, you know that the area of a circle of radius 300 is 2 pi times 300. And then if you're looking at traveling 1 degree along that circle, that's 1/360th. And you do a calculation, you get something which is about 5.2 feet. And in fact, that's correct to 2 decimal places if you just do that estimate. And this is the fact that, this is the basic message of calculus, is that if you look at a really small scale at a curve, it looks just like a line. So, okay, so that's pretty good. Now, what happens in hyperbolic space? Well, you could attempt to perform that same estimate, and you would realize now you're taking the circumference of the circle, which is roughly pi e to the 300th, and then you're taking 1/360th of it, 1 degree's worth of it, and that would be pi e to the 300 over 360. And again, that has more than 100 digits. So first of all, that tells you can't be more than 10 to the 100 feet from the hole, right? Because you started 300 feet from the hole, you only hit it 300 feet. You could be at most 600 feet from the hole. So this method of traveling along the circle in hyperbolic space is terribly inefficient. And so you can do a little trigonometry, which I don't usually do in the talk because it gets tricky, but it actually turns out that in this case, if you hit it exactly 300 feet and you're exactly 1 degree off, you're more than 590 feet from the hole. which means you're further, even hitting that good a shot in hyperbolic space, you're further from the hole than where you started.
Which is probably not good for people's golf games, I'm sure.
No, right. I have enough trouble, in Euclidean space.
Right.
Pretty much likely if you're playing golf in hyperbolic space, you hit the ball, you're further from the hole. You hit the ball again, you're even further from the hole. And it's
right.
going to keep getting worse.
Oh, yeah. So you're just never going to get there at that rate.
Yeah, pretty much.
Right. Yeah.
Think about what this means for walking around. You go for a walk. If you just go for a walk and you walk a few hundred feet, and then you take a right turn, you walk a few hundred feet, take a right turn. Unless you're very, very precise in these terms, you're going to end up further from home. You're never going to get back home this way. So if you just sort of, you walk 300 feet, make nearly a right angle, walk 300 feet, make nearly a right angle, walk 300 feet, make nearly a right angle. If your right angles were off by a degree, you're probably more than 1,000 feet from home.
And then you're never going to get back there, huh?
Yeah, then then you're in trouble. Yeah.
Right, okay, yeah.
And in fact, the next thing I usually talk about is beach ball, which tells you, in fact, even more why you're in trouble if you try to do this. Because if you think about it, this goes back to think about in Euclidean space, why do mountain ranges look fairly close to us, even though they're a long way away? You can say, well, it's because they take up a large part of our field of vision. And so, sort of when we see the things which take up some definite percentage of our field of vision. So if you think about sort of an idealized, think just in the plane, and we look at our field of vision, that, our field of vision is like half of a circle. It's a semicircle. It's our whole field of vision. That has length. The field of vision at distance r has length pi times r. So if you take a beach ball of radius 1 foot, and it's 300 feet away, you can sort of see a colored beach ball 300 feet away. I probably can't anymore, but younger people can. And so it's taking up about 1,000th of your field of vision. So for me, that's a pretty good estimate. If you're taking off 1/1000th of the field of vision, or 0.1% of your field of vision, you can probably see something. And if it's 3,000 feet, which is a little more than half a mile, you can't see that beach ball. So that's 0.01% of your field of vision. So you could say, well, if something's taking up 0.1% of your field of vision, you can see it. So, okay, what about happens in hyperbolic space, where your field of vision is size roughly pi e to the r over 2. So it turns out that you can't see that. So if the beach ball is 300 feet away, it's taking up, 1/10, less than 1/10 to the 100th of your field of vision. We're certainly not seeing it. And in fact, you can't see it till it's about 7 feet from you.
Does this have to do with the field of vision being so much bigger in hyperbolic space?
Vast. Your field of vision is so vast, so that since your field of vision, even 30 feet away, your field of vision has roughly 10 digits. There's over 1 million feet of your field. Well over 1 billion feet of your field of vision. Or even more than 10 billion if you're 10 digits, right? So 10 billion. And, just something 1 foot big is sort of just a total grain of sand in that 10 billion feet. So, but at 7 feet away, it's starting to take up about, somewhere between 6 and 7 feet, it's starting to take up about 0.1% of your field of vision. So
right. So you're basically saying that people are not blind in hyperbolic space, but close to it.
Right there, you're going to see only very, very large objects, and even a very large object as it sails away from you. So the Titanic, it's going to sail away from you, and after a couple hundred feet, you can't see it. So
right.
So that means, if you think about what that means for all these sports, that not only if you're walking around in hyperbolic space and you walk 300 feet away and you make a slightly not quite right angle 300 feet, not quite right angle 300 feet, and you try to come back, well, first of all, at no point during that process did you see your house. Because as soon as you got 10 feet away, 10 or 15 feet away from your house, you didn't see it. And so now you're 1,000 feet away from home and you can't see your house.
Right.
So you're in a lot of trouble.
Right.
Also, if you think about baseball, someone's throwing a ball at you at 100 miles per hour, you can't see it till it's 6 or 7 feet from you. So you never hit it.
No, but if it's you have to get it so accurate, it's probably never going to come to you anyway. Is
Well,
that?
see, that's the upside or the downside. The pitcher can't. So okay, you can't see the ball, but the pitcher can't see you, and so even if he's trying to throw it, even if he can throw it very accurately, he can't see you to throw it at you, and if he does try to throw at you, he's never going to be that accurate. So actually what's going to happen in hyperbolic, you don't really need any outfielders in hyperbolic space, right? Because no pitch will ever go over the plate, and it's just going to be a succession of walks.
Right, okay. Probably makes dodgeball not a very much fun game either.
Right, well, yeah, so yeah.
So one of the other things that you've talked about in hyperbolic space is the difference in triangles. I wondered if we could talk about that as well.
Right, so a characterizing property of hyperbolic space is that, these triangles have angles adding up to less than 180 degrees. Because if you see that, you imagine one of these, I think about what do we mean by a triangle? Well, the edges of a triangle are line segments. So these triangles will be made up from hyperbolic triangles are made up from hyperbolic line segments, and they all sort of bend in. So the angle they make is sort of less than the corresponding Euclidean angle. Or you can think about what happens on the sphere. You can also have spherical triangles, right? You can imagine that you take a latitude, which is sort of a great circle, and then you take the equator. And if you take two latitudes, which differ by 90 degrees at the North Pole, they come down and they hit the equator at 90 degrees. And so that you get this spherical triangle where the total angle is 90, 90, 90, 270 degrees. So this is sort of a characteristic of spherical geometry. And in fact, more generally, in a positively curved space, the angles add up to more than pi. It's like the sphere is a positively curved space. And hyperbolic space is one of the first examples of a negatively curved space. So another thing you can think of is the geometry of hyperbolic space is sort of a little bit like the geometry of one of these hyperboloids, where you see this sort of negative curvature. And there, the angles of triangles add up to less than 180 degrees.
Mm-hmm. And I think you've equated that to a soccer field in the past too, where you basically have a square that's two triangles. So how does that shape change in hyperbolic space?
Right. So an amazing thing. There's an amazing formula in hyperbolic space, which has got vast generalizations, called the Gauss-Bonnet theorem, which says the angle of a triangle is exactly pi minus the sum of its angles, where you measure angles now in radians instead of degrees. So that tells you that the area of your triangle is always at most pi. So a soccer field is played on a rectangle. Well, rectangles are made up of two triangles, so they have area at most 2 pi. So no matter how big your soccer field is, your total area is less than 7, or less than 6.29 even. Less than 6.3 anyway. Right. 6.128. Yeah.
Right. Okay.
6.28. Whatever. Anyway.
Around 6. Right.
I'm remembering pi. Okay, so that means, if you think about what that means, is that you can't fit an entire soccer team on your field even. And moreover, what happens is, even if you have this rectangle where these sides have length 100, well, what the hyperbolic lines do is they bend and they come very close to one another. So in fact, the borders of your rectangle in the middle are roughly e to the minus 50 from one another.
So you're talking about basically it looks like an hourglass on the sides almost.
Yeah, right.
Yeah. Right.
Yeah, I'm used to having a blackboard. Maybe I should have set up the camera so I could have done this all on the blackboard. That's how I usually do it. But anyway.
Next time.
So that means that if you kick the ball, it's going to be very, very hard to keep it in the field, because, well, the one chance you do have is that in soccer, the border is in bounds. But if the border were out of bounds, like it is in football, there wouldn't be even room for the entire ball to fit within bounds, and you kicked it from one side to the other. So.
Right. Yeah, it'd be hard to play that game. A lot of red cards, right? Okay, so we've only got about 15 minutes left, so I was hoping we could kind of switch gears just a little bit and sort of talk more generally about the mathematics field and where it currently is, if that would be okay with you.
Sure.
So what you were talking a little bit about this earlier, but math is needed in pretty much all fields of science, and I was wondering if you found mathematics to be particularly cross-disciplinary, or if there are ways that working with colleagues across different fields can help with increasing understanding or creativity within what you do.
Well, I mean, there's sort of, I mean, in some sense, two questions there. One is, I think, for someone like me, who I don't really work in areas which are very close to current interests of applied mathematics, but I still find it very useful to talk to people in nearby areas within pure mathematics. And I think that's something we're seeing more and more of, that the most exciting mathematics isn't in one field, but it's sort of, it develops interactions between several fields. And then you're also seeing more and more sophisticated interactions of mathematics with the sciences. And I think the field that you're seeing this most strikingly at the moment is mathematical biology. Sort of the ability, and this has something to do also with the development of computers, the ability to process very large data sets, and then the ability to develop much more sophisticated models, to bring more sophisticated mathematical tools to bear on it. You're seeing some very exciting things where biology had started originally in its roots is a more qualitative discipline, and now you're seeing a more quantitative side of biology developing. We have several mathematical biologists in our department, and they study things like, one works with the neuroscience department, doing things like studying sleep cycles, and people who model tumor growth. There's a lot of really fascinating stuff, and people who are able to work directly with labs, look at very large data sets, and then see how it works with their model. And you're starting to see a lot of sophisticated interaction there.
Do you think that having the interaction between the different areas of sciences can feed back into the mathematics itself and kind of open up areas of thinking that maybe mathematicians might not have considered as immediately on their own?
Yeah, I think so. I mean, actually, mathematics, of course, grew out of the sciences. Mathematics, I think when you look at something like Euclid, that's something which we would recognize now as pure mathematics. How do we develop geometry from the axioms? But most of what we now think of as mathematics grew up in service to other fields, in particular physics. All of calculus is really developed, study laws of motion, etc. And probably if you go back to the 17th century or earlier, there's not really a distinction between being a physicist and a mathematician. So, yeah, I mean, that's where mathematics comes from.
Right.
It's from the sciences. And, now I think there's, it goes both ways. There's contributions that the mathematics has made to the sciences, that they use tools that we've developed, maybe not directly for them, but they later turned out to be very, very useful. And I think that, that continues on, that sort of interaction. I know a lot of people in geometry topology, it's not so much true of my own work, but they draw a lot of intuition from physics.
Right. I think there's actually in the last couple of decades, particularly, maybe longer, I think there's been sort of almost a rebellion against the divisions in science. A lot of people seem to be going back to more of the original approach to sort of everything as a whole, rather than trying to compartmentalize different areas of science.
Yeah, I think traditionally, if you go back, when I was entering mathematics or earlier, there was a certain amount of hostility between, so-called pure mathematicians and applied mathematicians. And I don't think that's really nearly as present. I mean, obviously there's people with all sorts of prejudices still existing in this world, but I think as a whole, both the pure and applied community sort of realize that they're getting a lot out of interacting with each other.
Yeah, I was actually going to mention that we had an article in American Scientist a couple of issues ago about the famous pure mathematician G.H. Hardy, who was very proud of the fact that he'd never done anything that he said was useful. So I think that there's been this impression that there's a strong divide between pure and applied mathematics that the author of the article, Dan Silver, was saying was being blurred somewhat now, particularly because of the use of computers, but it sounds like culturally there might be a shift as well.
Yeah, I think it's, yeah, I don't really know what the roots of the hostility were even, but yeah, it doesn't make much sense to me that it would exist, and luckily I think it is going away. I mean, Hardy is in some sense particularly ironic because number theory is one of the most useful things now. I mean, this is what the NSA is essentially a large group of number theorists who work for our government decrypt, and because number theory is the major tool in decrypting and encrypting, so coding, and so for instance, a lot of our modern techniques of sending data securely over an internet are entirely based on number theory. The fact that that it's very difficult to factor a very large number into its prime decomposition sort of lies at the basis of a lot of modern coding theory.
Right. Yeah, it's funny how that has worked itself into modern culture. There's been popular TV shows that talk about sort of NP complete problems, which nobody would have understood before needing it in cryptography. So.
Right. Yeah. I mean, definitely. The computer culture has brought the sort of number theoretic thinking very much to the fore for a lot of people. Yeah.
I think there's also this sort of Hollywood idea that scientists and mathematicians are very isolated, which I don't agree with, obviously, but I think that's still an impression that a lot of people have. And you mentioned before about some of your most productive work coming from working with colleagues. I wondered if you could talk about, you're saying that a lot of the connection you do now is virtual, but if you can talk about the difference between connecting with colleagues virtually versus in person, if you think that virtual interaction is all you need, or if in-person interactions can sometimes be more productive.
I would say that virtual is a nice addition, but it doesn't replace. So for instance, in mathematics, a lot of the field proceeds, we have these conferences and we get groups of people together, and a lot of it is sort of semi-accidental. You get a lot of people with similar interests in the same room, and then all of a sudden you discover that there's some connection you didn't realize. And once I have begun collaborating with someone and we're focused on some issue, then it's great. I can have this kind of conversation, and maybe it's not so important to see them in person, but being in a conference together for several weeks, or several, not usually several weeks, usually several days or a week, and just hearing people talk about the recent advances in the field, you're talking to them, and there's a sort of thing that happens which you can't quite replicate virtually. There's human beings being together and just talking. You go to the talks and you're processing it, and then you're out, having a drink afterwards, and you're just talking and say, well, wait a second, I was thinking about that, and all of a sudden you've got something that you didn't know was there.
Right. So do you think a lot of the inventiveness or the advances are in fact this kind of spontaneousness that happens just because you've kind of put yourself in the right situation?
Yeah, I think there's a lot of serendipity to scientific or mathematical discovery, and you get the feeling that sometimes things were in the air, and if you look back at it in retrospect, you say, oh, well, someone was eventually going to make that connection. But when it was going to happen and who was going to do it, yeah, sometimes it's very much a result of, could have taken an extra 5 years if you didn't happen to both be at the same conference. And hey, you got your peanut butter and my chocolate, and
Right, right. Um, so I'm sure you hear this a lot as a mathematician if you go to cocktail parties or whatever people do. But a lot of people are probably still tell you, oh, I never liked math, or I was never any good at math. And there are still probably a lot of kids who feel that way. I wonder if you can talk about any advice you've ever given kids who've said they don't like math or they're not good at math, about how to get them kind of beyond that stigma.
I think the key, well, I mean, certainly with younger kids, is to put them in a situation where they can have success with it. A lot of people, because math is so hierarchical, a lot of people keep doing math until they fail at it, and then they just stop. So then their last experience is this very sour experience. They say, well, I used to love math, and then I got up to class X, and I couldn't do it, and whatever. And often they say they can't do it, but they could do it, but something didn't work out. It was, a bad connection with the instructor, or they weren't ready to do it at the time. And if you put them back in a situation where they can succeed, then all of a sudden they can get their positive attitude back. But there's a lot of, people build up a lot of, I think, psychological blocks to success in mathematics sometimes. They start telling themselves, oh, I can't do it, because their last experience was failure. Instead of like thinking, well, everything was fine up until then. 95% of the time I could do it.
Right. And I know this is way out of your field, but there's been a lot of debate about Common Core math, new ways that people are teaching math to kids in elementary school even these days, and parents having a lot of sort of balking at it because they don't understand it, or that's different than the way that they used to. But a lot of it's designed to increase your mathematical thinking necessarily than just problem solving. And I suspect that can probably help people become more accustomed to doing math as they go on, if they sort of develop their ways of mathematical thinking. I wondered if that was something you had any opinions on.
Right. So I guess my kids are now, out of school. When I was in school, I mean, there's been, of course, a succession of mathematical reforms, and so my kids were in high school about 10 years ago, and I thought there were a lot of interesting things done with really trying to get people to think about mathematics and getting to see, mathematics is not you just compute the answer is 37 and you write a circle around. This is something we focus very much on when we teach calculus here at Michigan. Is we want them to be able to write a sentence or a paragraph about what they've done. So if you do some calculation, you calculate some derivative, and you see it's 37 and declare success, and then if you ask them, well, what does that mean? They go 37. I say, well, does that mean the car was traveling 37 miles per hour at 6 p.m.? Does that mean you're 37 feet underground? What does it mean? Obviously, in real life, you got to know, what is that 37 about? So one of the things I saw in a lot of the things that in the reforms happening when my kids were young, we're trying to get at that. And another thing we're doing here at Michigan is we're really developing classes which focus on inquiry-based learning, which is a whole, actually I consider giving a Sigma talk on this. Inquiry-based, which is based on sort of techniques developed, which are closely associated with Moore. From Texas, we're getting students to really develop mathematics for themselves, and doing it in such a way that you're putting them in a position to successfully develop mathematics for themselves. And they start realizing that mathematics makes sense. They know how to think about it. They can work with that. For instance, we have a freshman course on cryptography where they sort of develop a lot of basic number theory really just entirely on their own with hints from the instructor rather than just being told everything by the instructor. And I think that's a really valuable side of what's going on now in mathematics reform.
Right. Now, for people who are sort of more advanced in their education, who are, in the graduate school level, I'm sure that going through a PhD in mathematics is just as rigorous as in any of the sciences. Did you have any tips or hints or sort of best practices that you can sort of generally give people for surviving the graduate school process?
I mean, I think it's important to make connections. A lot of times when I see people struggle, it's because that they haven't made use of the resources which are available to them. They're not reaching out to their fellow students and working in groups and talking to people. Sometimes, you know, I see people banging their head on the wall about something for a long time, and they're missing one little piece. And if they ask someone, they say, oh, well, how about that? And then they'd be able to move along. And also interacting with the faculty, getting into office hours. The same thing with undergraduates. Very few people use office hours as much as they should. I mean, we're sitting here, we're ready to help people, and people struggle on their own instead of coming in and getting that help that's available to them.
Right, okay. Well, we're out of time, so unfortunately we're going to have to leave it there. So I will just once again remind Sigma Xi members that if you have additional questions for Dr. Canary, you can post it into the Sigma Xi communities page. There's a thread there. Let's talk about Hyperbolic Space, where you can ask additional questions and we'll get them to Dr. Canary. But Dr. Canary, thank you so much for joining us and for helping us see the world in a different light. We really appreciate it.
Well, thanks. I enjoyed it.
Great. Thank you again. Bye-bye, everyone.